Hi, let me show you what we have done and what we will be examining next. We are dealing with the sequential circuit. Within this sequential circuits, one of the main element is the memory element. So we have seen these memory elements here, the basic memory elements or the fundamental memory elements. Those are the memory elements from which we can find out all the other four type memory elements. These are SR memory elements, JK type memory elements, T types memory elements, and D types memory elements. But we had a basic problem with these fundamental memory elements. That was the forbidden inputs. SR type memory element, the forbidden input is 1, 1. S star R star type memory fundamental memory elements forbidden input is 0, 0. So we said although these are forbidden, assume that we are not going to apply those, but in practice we face a problem because the allowed inputs, if we apply 0, 1 and 1, 0 allowed inputs one after another, because of the delay, there could be 1, 1 input or 0, 0 input. That forbidden inputs, although we don't want it, we might be applying it. So the solution to that problem, we said we are going to introduce a new input, which is called enabled. Sometimes we call it clock. If we use the enable input, we can solve that problem. So the solution of that problem became add 2 more gates and 1 input. So that was what we paid to solve that problem. Afterwards, we examined in this frame here, we examined the JK type and T type memory elements. In these memory elements, we have seen toggling problem. The toggling problem has not been solved as this, the previous solution is not a solution to this toggling business. And then we came in a position now how we are going to solve the toggling problem. Now I am going to explain to you this last frame here in 2 different videos. The first video is the solution to the toggling problem. The first 3 frames here includes these solution of the toggling problem. The last one is the commercial flip-flops, and I will be examining these commercial flip-flops in a different video. So let's start with this video now. Escape from this, and you see to the transition I've got to do some settings. Open board, let me open board, open the board, open board, and then apply these settings. Open board, open board. Okay, here we are. What you're seeing here is the general form as sequential circuit. Let's say general infrastructure of a sequential circuit. So these are the memory elements. So we said the solution to the first problem, we introduce a clock input or the enable input. Let me write it enable. And we've got a signal like that. Enabled signal. Like that. So I'm going to show you within this infrastructure the toggling problem, the problem that we face with JK type memory elements, T type memory elements, and this happens in here in a bit different way. So this has got a problem as well. This infrastructure, due to this infrastructure, there is additional problem again. What is this problem? You see this dotted frame here shows this sequential circuit. So how this sequential circuit works? So here we've got small y's. So I put in a, oh, so, okay, so let me change it. So red small y's here is the present state. And I've got an input for this present state. So if we know the present state and if we know the inputs, this combination circuit works. At the end output, I'm going to get inputs for these memory elements. How this is going to happen? This is going to happen on this edge. This operation is going to start on the jazz, because when the 0 becomes 1, my memory element is going to work, isn't it? So this red memory element inputs came to here in this time interval. When the enable input becomes 0 to 1, these memory elements are going to work. So I'm going to get a new state here, which is called next state. So this capital Y's are next state. Okay. So I am in this time interval now. So I came to that red capital Y's, the same wire as the present state's wires. So this green, and I haven't changed the input yet. Since this is a combination circuit, works independent from the enable input. Enable input is connected to memory elements only. So when this capital Y's came here, I haven't changed the input, so my combinational circuit is going to work again. Corresponding to this new state, I'm going to get a new memory element inputs sequence coming in front of these memory elements. Since I am in this time interval, so that means it is working. When it is working, this memory element is going to run again. Let's say at that point, that memory elements run again. So I'm going to get new next states. So let me show you this new next states in blue. I haven't changed my input yet. So I have got this previous input still there, but I have got new state variables here. My combinational circuit is going to work once again, and I'm going to get that blue memory element inputs here in this time interval here. So if you consider this time informal increases, so for the same input, state changes are going to be many times, depending on the length of this one duration, let's say pulse duration. So this is something we do not want to have. Why is that? Because our expectation is this. We are going to, our present state, apply an input, get this here, and get this next state green here, and stay there. Don't change. I am going to change this input to green, and then in this for this input, this next state is going to be my present state, and I'm going to work again. So that means one input, one state change, another input, another state change. We've got to follow like that. But it doesn't work like that. So that's the problem. It is similar to the toggling problem. So what is the reason of this problem? Is this time duration. So this time interval is the problem. Longer it is, more changes that I'm going to face with. So what type of solution you expect to make this minimal? How I am going to make it minimal? Ideal case is edges. What I mean by edges for the clock pulse, that is the rising edge, 0 to 1 change as rising edge. We call it positive edge as well. So this time interval, the transition time interval here is minimal. It could be either this one or 1 to 0 change. It is called falling edge or negative edge. So I'll show you here. You see this is the enable input. So this is the rising edge, this one here. And that one is the falling edge. So this one. So double star here and 1 star here. So the idea is this now. The solution to this new problem is to introduce edge triggered memory elements. So the next state is how you're going to make it. So that's the next slide here. So you see this is called master slave configuration solution to that problem. Master slave configuration. This configuration doubles the D-type memory elements. You've got one memory element, the one that we already seen, which has got 4 NAND gates in it, including the feedbacks as well, and another D memory element, and the first memory element, that's the master one, and that's the slave one. The first memory element enable input connected directly, and the other memory element enable input is the NOT of this original enable. So this brown frame is the T-type memory element, which has the property of working on the edge. So we are going to show now how it works on the edge of the clock pulse. So let me draw that clock pulse once again. Here. So let's examine what happens in this time interval here. In this time interval, this is enable. When enable is 0, that is 1, that is 1, 0, that's 0. So either you're here or here. So your enable if input is 0, that means that is 0. Not working is not 0. And the not of 0 is going to be 1, that's going to be 1. So working, this one is working. This one not working. So when this is not working, it is in the present state. So that is the present state of the first memory element, the first D-type memory element. So if this is working, this information, that present state, is going to be transferred to the output. So that's the present state. This happens when it happens, when the time interval is equal to 0. This happens. So when the time interval changes from 0 to 1, what happens. So we are in this time interval now, changing from 0 to 1. So that means that's going to change from 0 to 1, means that's going to change from 1 to 0. So when this change from 0 to 1, my memory element, this memory element is going to work. This is not going to work. So when I say this memory element works, here is the definition relation of this memory element, D-type memory element. I'll draw it here. D, that's small y, 0, 1. 0, 0, 1, 1, 0, 1. So we said this is going to work. When it works, this so mathematical model of this capital Y is equal to D, isn't it? So that information is going to be transferred to this first memory element output while this is not working. So that means we are in the present state for the second memory element, but for the first memory element, the D information is transferred to the output. So this is what happens here. Okay, this happened on this edge. But what I am trying to show here, to show that Brown framed circuit behaves as a edge-triggered memory element. So if we compare this output here, this Brown memory element output, no change here because it was present state, still in present state because it is not working here. So no change at the output. If I keep it in this time interval as 1, there's no change because this is going to be not working, and that transfers that T to the output of the first T memory element. So no change up to here. When now the critical point, when the enable input changes from 1 to 0, that means that's the case, that's the negative edge. What happens, this 1 is going to be 0. That means not work. When this changes from 1 to 0, this is going to change 0 to 1. It's going to be working. When it is working, this D, which has already been transferred from the first one, is going to be transferred to the output. So here I'm going to observe this D input at the output of my D memory element. That is the definition relation of this memory element, isn't it? So what happened is this. If I consider this Brown framed circuit, this circuit worked on this time interval. That means falling edge triggered. So this is what I expected, isn't it? Falling edge or negative edge triggered. So call this flip-flop. D-type flip-flop. This D-type flip-flop, that brown one here, behaves as a D-type flip-flop. And this flip-flop works on the negative edge only. It doesn't work the other time intervals for a given enable input. So you see here there is another configuration, master-slave configuration for the SR-type memory element. How this SR-type memory elements work as a falling edge sensitive memory element, you do the analysis your own, and I left it to you. So let's outline what we have done here. We had a D-type memory element which has, let me write it here, 4 NAND gates in it. So I've got a toggling problem and the general problem that I explained already. Solution to that became 4 NAND gates in this D-type memory elements, another 4 NAND gates in here, plus this NOT gate, altogether NAND gates. NAND gates. The cost of this solution, NAND gates, plus I had only one D-type memory element, which has, if you assume that the delay time for this D-type memory element delta t, then since I have used 2 D-type memory elements in here, I have got 2 delta t here. So the delay doubled. So my solution increases my costs by this and also make it slower than the previous one. So the next step, another engineering problem, can we reduce those two on we are unhappy to see this cost increase in engineering point of view. It's not good news. Delay increases. This is another engineering problem which is not good news for an engineer. So how we can we reduce these two? That is the subject of the next frame. Let's come to this next frame. So you see here there is a once again brown box here. We are saying that this brown box here is a edge sensitive D-type memory element. So how many gates we've got here? Just let me tell you the benefit of this configuration. In here, instead of 9 gates, we've got only 6 gates. So we reduce the number of gates in it. And on the other hand, in the previous one, we had delta t. So that means here, so 2 level here, another 2 level here. The total level is 4 level. So when I say delta t, 4 level, let's say. Now when you come to this one, it is only 2 level. So 4 level transferred to 2 level. So that means increase the speed. We doubled the speed, or make it half of the delay in the previous case. Okay. Now how we have done it, we've got an R star memory, fundamental memory element in here, and we've got at the input that configuration. Now what I am trying to show here to prove that I have got a D-type memory element of which definition relation is this, which is this, isn't it? So I'm going to consider this brown frame circuit behaves as this. In addition, this is edge sensitive. So let's show it now. How I am going to show it? Before we start, let me to explain something. This is a star R star fundamental memory element definition relation. So that means definition relation of this element. So the output of S star R star memory element output is this. This output is also this brown framed D-type memory element. So this output is S star R star memory element output, at the same time D-type memory element output. So I am going to show you now this Brown frames circuit behaves according to the D-type and it is edge sensitive. So in order to do that, we consider here the first level only, first level only, first level only. When the clock, so I have got a clock input. So let me draw this clock input once again. Let me make it in different color. Clear that. So that is, oh, okay. My clock input or enable input. So how I'm going to examine this? So you see the first level, clock input is 0. Clock input is 0 means this time interval, and this time interval is none. What happens in this inputs, S star R star inputs, while when D equal to 0? So I am trying to prove the Brown frame circuit behavior when D input is 0 is according to this definition relation. So let me prove it. So D equal to 0, clock is 0, without looking at the other inputs, clock is 0, whatever the other inputs are, multiplication gives you 0, the complement of this multiplication gives 1. So both of those S star R star values are going to be 1, 1. When this is 1, not important what it is, since D is equal to 0, that's going to be definitely 1. This one and that one, that's going to make this 0. So what I am going to see in this time interval 0 is this when D equal to 0. So I'm going to observe this here. Okay. So what it means, S star R star 1, 1 means you are in this column. So if you look at this definition relation, it tells me when the S star R star value is 1, 1, there's going to be no change. Whatever the present state value is, the next state value is the same, and same here. So no change, no change. Let me write here. So in here, no change, no change. When I no change means state is not going to change. Okay. So let's jump now from the clock 0 to clock 1. So where I am now in this time interval. Here, 0 to 1 change. 0 to 1 change. Still, I am in this column now. D equal to 0, isn't it? D equal to 0. D equal to 0. My clock is going to change from 0 to 1, so in here. So what happened at S star R star values? Let's examine it now. When the clock is 1, in here, when you make this clock is 1, so that means that is going to be 1, that is 1, that clock is 1, 3 ones multiplied, you get 1, prime of it is going to be 0. This 0 keeps that 1 as it is. Why is that? Because 0, whatever the other input is, that's going to be 1, isn't it? No change here means the feedback comes here from that 1, that keeps that 0 as 0. No change here. So no change here, no change here, but there is a change here. It was 1, it became 0. it happened in this case, like here. So what it means, S star R star column is going to be 1, 0. So we are in this column, right? While you're in this column, S star R star fundamental memory element state becomes 0, isn't it? Whatever the present state is, your next state is going to be 0. As I said already, this output here is the output S star R star fundamental memory element, but at the same time is the output of the D-type memory element. So it is going to be this, isn't it? So that means my D-type memory element worked on this edge according to the definition relation of D-type memory element. So what happens afterwards? That means after, if I keep this one value as it is here, so that means that's going to be 1, so this is not going to change, isn't it? If this is not going to change, you're going to stay in this column. So that means you're going to stay in this state, no change. It changed on this edge and kept that value as long as this pulse duration is equal to 1. So no change here. So what happens when you change from 1 to 0? That means you're going to change. Let me use another color, that blue color. So if you change the clock from 1 to clock 0, so that means this type of change. So that means this change. What happens from here to here? So we were in here, weren't we? So we had that green here. When you change the clock 1 to 0, you're going to observe this. So that means you're going to observe this, isn't it? After you change 1 to 0. When you observe this, that means no change. So no change here, no change on this edge. No change. What we have shown here is this. When D input is equal to 0, my memory element changes happened on this positive edge only. For the other time intervals, including this negative edge, there's going to be no change. So that means I have showed that this D-type memory element definition relation is true for D equal to 0 as the positive edge triggered. So what about this? That means, is it also true for the input D equal to 1? So D input to 1, make a yellow then. D equal to 1, D equal to 1, D equal to 1. So examine the D equal to 1 for this time interval. Clock is 0. So that means this is 9. So clock is 0. Whatever the other input is, when this is 0, the other inputs multiplied gives you 0. Prime of it is going to give you 1. When this is 1 and that is 1, keeps that 0 as it is. That 0 comes here and stacks that output to 1. The output value of this NAND gate is not important once the clock is 0. Multiplied 0, 1 gives you 0, prime of it gives you 1. So when the clock is 0, when you are in this time interval, in these time intervals, your S star R star memory element output is 1, 1, isn't it? Here you are. maybe not seen here. Make it a bit bigger. So S star R star is 1, 1. So that means you are here. So that means no change, isn't it? So when it is 1, 1, present state and next states, they are equal, no change. So this is a critical point now. If you change the 0 to 1, so that means d equal to 1, you are doing the raising edge or the positive edge. So that means you're going to change from clock 0 to clock 1 when d equal to 1. See what happens. When this is 1, that was, so you make this 1, that was 1, that is 1, 1 multiplied 1, 1, prime of it gives you 0, isn't it? So that's going to be 0. So when you make this 1, that was 1, and that was 0, whatever the other inputs are, although I said clock is 1, 0 to 1, because of that 0, that's going to be 1. So that is not going to change. So it is not going to change. My d is already 0. So 1 time 1 gives you 1, prime of it gives you 0. That is not going to change. It's stuck at 0. So since this stuck at 0, this is also stuck at 0. So when your clock is 1, 1, 1 makes it that 0. So what happened is this. On this positive edge, my S star R star values became 0, 1. So that means this one is net. So on this positive edge, I moved for the S star R star memory element from this input to that input. So for this case, it says whatever my present state is, my next state is 1, 1. That is the output as S star R star memory element. This is also the output of D-type memory element, which is the same, isn't it? So that means we have shown that enable input raising edge or positive edge, my brown framed D-type memory element works according to D-type memory element definition relation. So that is now works here. No work here, no work here. Or no change, you might say that no change we said here. So if you keep it as 0, if you keep this clock 1, that is going to be, that's not going to change, isn't it? So if you keep these inputs 0, 1, no change you're going to observe, no change you're going to observe, no change here. So for the yellow one, no change here. What about 1 to 0 change? That means negative edge change. So make it different color. What happens in this change? So that means you're going to transfer the clock 1 to clock 0. So that means this change, isn't it? So when you this change, you're going to observe 1, 1 again. So that means you're going to come back to that 1, 1 again. When you come to that 1, 1, means your present state is the same as the next state, no change. So that means no change here. And no change was already here. So conclusion is this. At the end, this brown framed D-type memory element behave according to the definition relation of D-type memory element on the positive edge of the enable input only. It doesn't work in other time intervals. So it worked in this time interval, that means positive edge, but not work on the other time intervals. That is what we wanted to have. So conclusion is this. So this is a flip-flop, D-type. That means flip-flop means edge triggered. And the cost of this D-type memory element is less than the master-slave configuration, because it was this 9, we transferred it to 9 to 6 gates. On the other hand, we had 4-level configuration, a 4-level delay in the master-slave configuration. In this configuration, we've got only just 2 level. So we doubled the speed, that means, and we reduce the cost 1/3. So that's the good news. That's the end of this video as well.